A better method for finding roots of equations is the Newton-Raphson method. It is considered the best method as opposed to the incremental search and bisection that we've seen earlier. It is simple and relatively fast in terms of converging to a very good approximation to a root. However, it does require information that's not necessary with bisection or incremental search, and that it requires information about the derivative as well as the original function f of x itself. So you must have the derivative f prime of x as well as the function itself to be able to implement the Newton-Raphson method. Its derivation comes from the Taylor series expansion of f of x about x, and specifically we'll write that Taylor series expansion using this particular formula here, where we're representing it in terms of our iterates that will hopefully converge towards the root. And we'll write it in the sense that the function evaluated at our new point xi plus 1, given that we are currently at xi, would be expanded using the current functional value plus this additional term f prime of x at xi, and then plus itself multiply the difference between those two plus an order xi plus 1 minus xi squared term. That's just using the fundamentals of the Taylor series expansion. Now, if xi plus 1 is a root, then of course that means this term right here would actually be 0 if we actually got to the root by this method. So in that sense, we would have this equation here, that this right-hand side would be equivalent to 0. So if we take that equation, and let's assume that we are getting closer to the solution and that there's very little difference between xi and xi plus 1, then we can drop that extra term, the order xi plus 1 minus xi squared term that we had in that previous equation, and now we would have this relationship, right? So that we would have that 0 is equivalent to f of xi plus f prime of xi times xi plus 1 minus the derivative at xi times xi. We just rearrange those terms using that this is 0 on the left-hand side. We produce this iterative method, which is the Newton-Raphson formula. Again, we're just using algebra and dropping that higher order term in the error associated with using Taylor series expansion. And this is a new method that would hopefully converge to the root. And again, you would have the function available, but you also have to have the derivative available. Right? So if x is the exact root that xi approximates, then the error of what this iteration would produce, and in terms of how close it would be to the original, to the exact root x, we could specify it as e sub I and represent the error in the next iterate according to the formula that'll be on the next slide. So the error in the next iterate would be given by this particular form, that you can show that the error in your associated with your new approximation is a multiplicative factor times the error that you had with the xi term squared, and the multiplicative term is this ratio, the second derivative at xi divided by 2 times f prime of xi. So what's really important here is this is a representation of the error at xi, and this again is our representation of the error at xi plus 1. So it's telling you that what you're essentially able to do is reduce the error, okay, hopefully, in a quadratic way, hence the fact that this power is 2 here. So we say that this method converges quadratically. in the sense that the number of significance digits in the current approximation doubles. You would get double the number of decimal digits in accuracy every iteration, so that it would converge very quickly. When you get 2 digits, the next iteration you would get 4, the next iteration you would get 8. You'd be doubling the amount of accurate significant digits in your estimate. Okay, and again, just like we had with incremental search and bisection method, you are still using some tolerance value to stop, so that when the iterates become relatively close up to a value of epsilon, you would stop. Now what I've drawn here at the bottom here is a really nice geometrical illustration of what Newton's method does. Remember, we drew sort of a pictorial version of how bisection works. If this is a representation, the blue line here is your function, and clearly it has a root at this point right here, which we're trying to approximate. If this is the current iterate for Newton's method, and again, just keep in mind that Newton's method suggests that if you want to advance the solution, xi plus 1, you would do it from the current iterate that you have, xi, minus the ratio of the function at xi over the derivative at xi. Okay. So that's what the Newton-Raphson method is. And so this pictorially is showing you how you would get the next iterate. Graphically, what it means is at your current iterate, you would look at the tangent line to the function at that point, xi, and then use that tangent line as it intersects the x-axis. The point at which it intersects it would be your next iterate. Okay, so this represents the slope of the function at xi, and we know another name for that, and that is the derivative. Another way to verify this geographic argument is just to take the Newton-Raphson iteration equation that we have here, and what I've done is just solve, if you were to solve that for f prime of xi, in other words, just coming up here and saying, well, I'll just subtract xi from both sides and get this particular equation here, and then cross and multiply, divide through appropriate terms, take into account the minus sign there. You're basically saying that f prime of xi is this ratio. Well, keep in mind f prime of xi is the slope of the tangent line at that point, and that slope can be represented as the rise over the run. The rise currently obviously is f of x of I, that's how high you went, and the run, or that slope, would be going from xi to xi plus 1, written this way, at that difference. So it is another way of verifying the fact that what we're really trying to do is find the intersection point of this tangent line, using the fact that we can represent this slope using values of the function and just movement along the x-axis. So it's a really nice technique because the tangent line follows the direction of the curve in a much better way than just simply looking at guessing at where a function changes sign between positive, negative, or negative to positive. So the algorithm, pretty straightforward, works in the following way, as indicated on this slide, that you have to have an initial guess for the root. You have to start somewhere, like most iterative methods. The more information you have about potential root, the better off, but you have to start somewhere. And then you will simply compute the ratio of f of x to f prime of x, and then take that as our increment to the solution, and just update your initial guess in this way as x is x plus delta x, and just repeat that until the difference between the iterates, in this case represented as delta x, is less than some user's applied tolerance. But then this method converges quadratically, given the relationship between the error terms. The reduction is in terms of the square of the current error. There are cases when this method will not converge. or another way of saying that is that the method diverges. It does not get closer and closer to the expected root. And what's indicated here is sort of a typical case, especially if your initial iterate that you've chosen happens to be very close to a maximum or a minimum of a function. Now, if you think about Calculus 141, when is the case that the function itself would attain a maximum minimum? What's another way of describing that? Well, that's when the derivative is close to 0. And keep in mind, we are dividing by a derivative term there. So when that gets close to 0, this method is going to break down. You're going to be essentially dividing by something that's very, very close to 0, and the delta x is going to become huge and blow up. And this is sort of indicated here that the tangent line near a relative minimum or a maximum is not a good indication of what the function is going to do into the future. Clearly the root we're seeking here is there, and choosing this as initial guess is a problem. If we had chosen, say, this point as the initial guess, then the tangent line would have done us a lot of good. It would have been a better indication of the direction of the function, and it would help us find the root in a much faster way. So it's problematic in terms of where that initial guess is. Some people would say if it's not in a good neighborhood of the root you're seeking, it may not work. And the argument is that this is not really in a good neighborhood of that root right there. So we will look at the Newton-Raphson .py Python script that would implement this method in the textbook, pages 158 and 159. Again, I will also make this available on Blackboard for your testing and use. It does assume an initial interval for the root. In other words, we've sort of isolated two endpoints on the x-axis where we think there's a root. If it wanders outside of that root, this particular method is kind of fairly clever that you can use the bisection method to get back closer to the root, sort of to get back into a closer, more narrow interval where the root is. Also is another particular case where the Newton-Raphson iteration would not converge, and this one's kind of subtle, but it's also kind of interesting. If the root indicated here, the blue curve here is your function f here, and if the root is near an inflection point, where the derivative is changing, so this clears the root. If you were to take a guess, which is reasonable on one side over here, and again look at the tangent line at that point on the curve at x0, continue down, and then that would be our next x1. Then look where the function is there, and here it is down here, the blue. Again, use the tangent line to find the next x2. What you're going to do here is spiral completely away from the root. So this is another case. You would have to be very, very close to that root. In other words, this x0 needed to be very, very close for that tangent line to be more reflective of what the curve is doing near this inflection point. So again, that's two cases, very special cases where you could run into trouble. And this is a case where in the software we'll see that if you do wander out away from the root, perhaps we need to use bisection to get, to restart this and get much, much closer, a much closer bound in terms of the original endpoints of where the root is. So here's the Newton-Raphson Python module that is found in the book on pages 158 and 159. Again, this sometimes called a safe version of the method assumes that the root to computed is in a bracketed interval AB. And the midpoint of the bracket is used as the initial guess of the root. So it sort of starts off like a bisection method. And the brackets are updated after each iteration. And if Newton-Raphson does not stay within the brackets, it's disregarded and replaced with bisection, right, to get back closer to the root. So in the docstring here, again, you would need a function, but not the original function f, but you also have to have its derivative. It'll be denoted as df as the parameter here to the Newton-Raphson routine. Then the initial interval that you feel that the root lies in, and then our epsilon tolerance for determining convergence based on how close two consecutive iterates are. So again, this is a method that combines Newton-Raphson with bisection. If we just sort of look at the structure of the code just quickly, and then we'll use this in an example and run it for you. Again, this is provided on Blackboard. Again, if you're given an interval where you think the root is, the first thing to do is to check the inputs, because you may be if you are at a root on either of those cases, you're done. So evaluate the function at A. If it's 0, return A. You're done. If you evaluate it at B, call it f of B, test it at 0, return. So we'll make the assumption that neither endpoints are the root, and then we will check to see if the sign is the same. If the sign is the same for both A and B, we're going to conclude that the root is not bracketed, just like we started bisection. We want to guarantee absolutely that there has to be a root in there. And that will be what we mean by bracketed. We'll guarantee there is a root. So, so we'll assume that for this to continue on, that the signs must be different between f of A and f of B. One's positive and one is negative. So that there is a root, we'll take the midpoint as our initial guess, and then begin a set of 30 iterations. So this is a hard-coded number to allow Newton-Raphson to iterate. You could argue that maybe that could have been a parameter in the parameter list to define how many Newton iterations you're going to do, but we'll just leave it as it is, as the book has done it for now. Hopefully it would converge. It should converge relatively quickly if it's going to converge at all. Again, for your first guess is the midpoint of the interval AB. Test to see if it's 0. If it is 0, return immediately. You don't even need to do another step of Newton-Raphson. If that's not the case, then we'll tighten the bounds by adjusting the interval. Since we halved it, we'll work on the appropriate half to continue the iteration. And then the rest of the code is very much looks like a Newton iteration that we've defined based on our formula. You would compute the derivative there. So again, you're calling a user-provided function df of x to get the derivative there. And then with our try block, we'll compute the ratio of the function to the derivative, and then do our appropriate update, checking for possible 0 divisions. All right. And then update or iterate. And then here's the idea that if the result is outside of the brackets, if it pushes you outside of AB, we'll use bisection to get back to sort of to decrease the amount of the increment and get back into an interval. So it's a fairly sophisticated method. And if it can't converge in those 30 iterations, just print out too many iterations. It never, it's not going to be able to. We can't return an estimate where if it satisfies our tolerance, then we would be able to. So if we continue on down on this final page in the book of that, you'll see the example that we're going to do with this is to find the smallest positive root of this 4th degree order polynomial, as indicated there. So in the book, for this particular 4th degree polynomial, if it was sketched between 0 and 5, so you'll see the x-axis here indicated from 0 to 5, you can see from the shape of the curve that this, if the origin is right here, this is 0, 0, that it looks like the root is somewhere around 2. So, that will give you an indication of maybe where you might want to take an initial guess, or to say, I can get a nice bound between 1 and 3, or any adjustment you like to make. So this is sort of how you would run, set up your Python script to use the Newton-Raphson function. You would have to define the function itself, and you could do it as a one-liner by just defining a function that returns this, this logic here involving powers of x. And then you would take the derivative, as you would do in a regular calculus class, and then recode that as a new function and call it df. All right, and then of course, this is for this particular problem, we're defining Newton-Raphson in a very simple way by just taking out the bisection point altogether and just simply using a Newton-Raphson iteration that's pure in the sense that you just start off with your initial guess, add the increment based on the ratio of the function to the derivative. Of course, that is subtraction there, so it's really x minus this ratio, but either way, you can add dx where dx is negative. And then we would know the number of iterations by looking at where I was when it converged, and so the call would be something like this: root number of iterations Newton-Raphson 2.0. So all this function needs to, this particular implementation Newton-Raphson, without using bisection to to pull the root back in, simply just give me your initial guess. Here's the tolerance, and I'm going to return for you the root and the approximation to the root and I, which would be the iteration count. And here's the output for running it on this particular problem. You can see the root is around 2.1, very close to it, and it converged in 22 iterations. Now this is the example 4_7.py file that I'll provide for you on Blackboard, which matches what the book had. Again, in this particular example, we're defining a very simple version of Newton-Raphson without using bisection, for example, to correct for the wandering off of the iterates. I will provide you that Newton-Raphson.py file, which is that hybrid method on Blackboard as well. But for this particular case, it's very simple enough just to see how the pure Newton method works on this quadratic, on this quartic, in other words, this fourth degree polynomial. Again, here's the function f, and here's followed by the definition of the derivative. And here's the very simple iteration for Newton-Raphson. What I'm showing you is three illustrations of its call. In this case, that we'll choose an initial guess of 2 for the root, and then we're going to choose 0, and then we're going to choose 3. So I want to choose 3 different starting guesses for Newton and see what the effect is on the number of iterations. So again, each time we call Newton, it's returning a root. That's the x there, and it's returning the number of iterations, which is the internal I index variable in the for loop. So let's just run this and just see the effect. We know what the root is. We've already seen from the book it's around 2.09, close to 2.1 is the root. So if we go ahead and run this code, you can see what we get. The initial guess of 2, it gets very, very close. I mean, it's an excellent approximation to it, with a little bit of error out in these terms, but in 5 iterations, very fast. Farther away, we can pretty much get a good estimate, but it took almost twice as long. And then you could see even farther out to the right-hand side, it can get back to the root, but it takes much, much longer. So convergence is dictated by how good the initial guess is, and this problem clearly illustrates that.